So I'm going to cover these bits, a bit about animal dynamics, the engineering challenge they've got, why we were looking about model-based systems engineering, and then another things, not particularly in order. So who are animal dynamics? Well, animal dynamics span out of the University of Oxford in 2015, really built around a really strong idea that insights into biomechanics, coupling that with cutting edge engineering and software that's really become available over the last few years, really will help us to have much better insights into the way that unmanned platforms could be more efficient and robust, really by looking at how animals' control surfaces work. So it's not about biomimicry. When we weren't ever about trying to create a super efficient bird or a super efficient fish. It was about making man-made systems far more efficient. And we were doing that really based around three key things. One was questioning key assumptions, such as the propeller being that universal solution to propulsion, whether it's on water or in the air, or wheels over land. Secondly, taking inspiration, as I've kind of really already mentioned, from analysis of systems that exist in nature, coupling those with some computational analysis advances, and really being able to create deep insights into how performance gains might be achieved in unmanned platforms. And thirdly, using that understanding to develop products that really could be game-changing in areas such as humanitarian aid, emergency response, conservation, and of course, defense and security. And systems engineering became a key focus for Animal Dynamics, and they invited me to create a systems engineering capability starting off in December of 2019. But of course, there's some real challenges around that. It all sounds exciting, but you've got the challenges of complexity hit you when you go through the door in these things. And there are some hard engineering ones to start with. So we talked about these advances in unmanned platforms, but the reality of it is we've got to build a remotely piloted air system of, say, 250 kilograms plus. We want it to have safe, fully autonomous, beyond visual line of sight. It's going to be built around a parafoil glider, but it comes with 1,600 safety requirements imposed by the regulator. Because, of course, the regulations are exactly the same at the starting point that apply to something like a 737. There's other complexity too. We started off from a very blank piece of paper. The systems engineering department when I arrived was one. That was myself. We kind of doubled inside. There were about 50 people within the business at that time, 50, 60 people. No engineering processes, so not even a mechanical engineering process, no software, no embedded systems processes. Really, we were, to all intents and purposes, an extension of a university research department. So a number of things that you see on the screen there that we'd have to address. So my thinking going into this was, right, okay, where do I start? What do I start on? What is the time to market period that I've got? You know, when is this idea? It turned out to be about 3 years. What business performance expectations were going to be imposed on me by the head of engineering and the executive management team? And really importantly, down in the bottom left-hand corner, the bottom right-hand corner that you'll see, is how do I get appropriately skilled systems engineers into it, and not too many of them. Well, I took a stance that said, right from the outset, I'm going to go down a model-based construct for systems engineering. So as most engineering disciplines, certainly mechanical, has been really computer-aided design, computer-aided manufacturing for probably 30 to 40 years now. This is fairly new for systems engineering, really kicking off only about 10 years ago. And it's really only in the past few years that the tool sets have got to any degree of what I would call almost really workable utility, where you can really kind of see we're getting close to being able to have really good data exchange of engineering data across various different disciplines. And I really wanted to be model based around how we did system requirements, how we were going to analyze our system. I wanted data exchange between what I was doing in system design and the model control guys that were working for me in dynamic flight control, as well as integration, verification, and validation. And I wanted it throughout the whole life cycle. I wanted to be completely unreliant on formal documentation, albeit that you don't really get rid of documentation. That'll come clear in a minute. And there were some clear business benefits that I saw with this. And for those of you who are aware of model-based systems engineering, none of this really be unique to you, but these are sort of expressed in terms of what was really beneficial to us inside Animal Dynamics and what I was giving to to my people. And that was really that there was no defined systems engineering approach. We really were starting from a blank page, no documents, no process set possible. We needed to introduce more rigor, not just in the way that we were doing systems engineering. We needed systems engineering, but we really needed to come away from that kind of research department mentality if we were going to realize a product into a highly competitive marketplace. But we wanted to do it incrementally. It wasn't really an imposition right from the outset. We really needed more structure, and not just over the architecture and our behavioral representation analysis, but really right across the whole way that we did engineering. How were we going to do an engineering? Full stop. How we were going to structure our engineering department. And then traceability, and again, not just as it says on screen, but how could I provide an evidence base and an argument that would satisfy a regulator that I had fully addressed the design safety target that had been imposed on me, all the way down to component or even fastener level for that matter. Also, I spoke about that you don't truly get rid of documentation, and probably nor should you. The regulators like to do things in documents still, so where possible, though, I wanted to part automate that. I didn't want people typing up wordy Microsoft documents. What I wanted to do is I wanted the tool set to part automate that by creating templates within them. And all of this over time, and it is over time, this doesn't come up front. And I identified and put a case that would really deliver some benefits to cost, quality, productivity, and really importantly, our competitiveness. But there's an additional really key engineering target in that for me, and that's that last bullet point there, which looks at increasing the potential for design reuse. What is clear when you're looking at some of the systems we were looking at, whether it was a nano UAV of, say, less than 200 grams built around some flapping wing technology, or the parafoil glider concept that you see on the screen now, a lot of the system functions are broadly identical. And if we could capture them and model them in a consistent manner, we could reuse those models rather than starting again. So future projects would inherit the design intent right from the outset, and then specialize for the conditions that they had to meet. But you can't quite dive straight into the modeling. You don't get a tool, you don't dive in there. You've really got to understand what the systems engineering capability or the engineering capability you need is before you get really down that pathway. And a bit of a busy slide here for you now. When I originally gave this presentation to a conference back in November, they gave me twice as much time as the master has given me tonight. So I've condensed this a bit from 3 slides to 1. And the way to read this slide is looking from top to bottom. The top layer above that upper dotted line really looks at a capability level. So that's me as the head of the function there. What do I need to have as my building blocks? The middle layer, the application layer, or the application level, is looking at how and where I deploy that resource, that competency, and what needs to go along with it. And then that golden thread, the golden arrow running from top to bottom, is what do the people look like that I need to bring into that capability to ultimately deliver it using those processes, tools, and technologies. So that starts with the top left-hand corner there of a clear sense of the engineering strategy, the strategy for the business in terms of product to marketplace, the allocation investment that I'm going to be given to be able to run with this, and that's not just the people or information, it's finance, it's technology, tools, the logistics, the infrastructure, and the processes that I'm going to need to develop, and the skills that we're going to need to both bring into the business and mature over time. And that really led me to identifying 3 building blocks. Now, in reality, these are building blocks in a management sense and an allocation of resource sense. When you look at deploying it, you're deploying it as a holistic capability that's interoperable. So for me, that was built about a model-based systems engineering, really around architecture requirements and design, model-based modeling the simulation and analysis of flight dynamics, flight control, and then the integration and system validation. Now, how do we bring it all together? How do we know that we built it right? And more importantly, how can I prove it's safe to operate and it meets the regulators' requirements? And I've built it right. And that falls down into the middle, which starts to think about the competency I need. And this is not the competency of the individual engineers, it's the competency of the capability. So that really starts to think about, over the left-hand side, the technologies, the processes, the standards, the regulations, and the tools that I'm going to need. And on the right side, how I'm going to deploy these groupings of engineers into the business. So the deployment was going to be firmly on a matrix based. I would own the capability. I'd be responsible for the skill and the competence set. and we would deploy a team of systems engineers into each of the projects in turn as they kicked off. And that then leads you down in that golden thread down into what do the individuals look like? What do you need them to bring to the party in terms of their individual knowledge, their experience, their ability, versus those values, attitudes, beliefs that we really were bought into within Animal Dynamics? Did you really get the ethos of the company and what we were about to do, what we wanted to do? Then taking stock. So this got us to about March, where I stepped back and went, right, okay, kick this off in January. We're moving at pace. March time, what have I got? Well, I've got my business and engineering benefit now down. That's gone to the executive. I know where I am. My capability requirement has been talked about with head of engineering, the chief operating officer, and it's funded. The human resources team know what I'm looking for in terms of recruitment. And whilst I haven't shown you the slides alongside this, we were writing and crafting a process set that we set through as well, and we actually submitted as part of our 9001 reaccreditation in early April of 2020. And that really sort of reinforced, yeah, we're happy that we're on the right approach. It's going to be model-based. This is the cut-off point for model-based or not. It's going to be model-based. We're still happy with the benefit. We're still happy. We now know the system that we're going to develop as our first product. So we start thinking about how we get into model-based engineering now, model-based systems engineering. And the template I used for that was really simple. It's really 5 packages. It starts with looking at the regulations and standards. So I know what that is by now. I know that I'm broadly going to take an ISO 15288 traditional systems engineering standards as the underpinning basis for the development of my processes. But I also know by now the regulations that I'm going to have to meet. I know already that as it's going to be a 250 plus kilogram vehicle, that I'm going to have to comply with high integrity software systems that gives some very, very stringent regulations to us. It's going to be some very serious software constraints placed on us. So I know what my process set. I know the architectural framework that I want to put into the models. We took a view that said, by this time I'd recruited 2 people to work alongside me, and it was clear that we wouldn't have enough time to develop an internal architecture framework to set up our original models. So we looked around in the marketplace and looked at an open source architecture that had been created in France by originating in the École Polytechnique over there, called Cézanne, mathematically underpinned, and it had the degree of rigor. It had been used by the likes of Airbus and Thales in France as well. So we were happy with the provenance that it could stack up to what was clearly going to be quite a highly regulated regime for us. That incidentally have never regulated a parafoil type drone. When you look at the regulations at the moment, they apply to fixed wing or rotary wing aircraft. Nobody's ever written a regulation around a parafoil glider type drone yet. So we were going to be challenging, but we really wanted to work with the regulators. We wanted to explain why we didn't think it applied to us, but what should probably apply to us. Again, then looking at this thing called Ontology and Viewpoints, and this is a modeling thing where we look at ontology as what the set of definitions, artifacts, all the things that need to be within the structure of the model itself. How do we bring it all together? And what were those viewpoints? What were those stakeholder windows that we needed to represent in the model? What needed to be in there in respect of what we would call a set of views? So the type of diagrams that you then ultimately see when you look inside a systems engineering modeling environment. We then have to start thinking about the notation. What we're going to use to describe it. And in a systems engineering sense, there are a number of options really. There's what's called the SysML or the system modeling notation, or the unified modeling notation, which is really sort of, and SysML developed out of the UML. It's an extension of UML really being about software. And there's some really key advantages for going down that route in that they both conform, both regulated by an international standard. So again, we can demonstrate to regulators that what we're using in a modeling environment is equally as robust as the standards and the process set that we're using that's gone through these regimes. And at that point, we can start to think about, okay, I can now go and buy a tool to do all this with. And again, it wasn't just looking on the market. There's lots of tools you can get out there. They can range from being open source and free at the point of downloading. There is a cost to all of this, obviously, or incredibly, what I would call advanced tools that you really need some subject matter experts with that would probably be on the affordability that I was able to operate in. But it's not just talking to your systems engineers. You're going to share this data with mechanical engineering software, embedded systems. In fact, my intent was to try and bring software and embed it into this tool environment themselves. So we spent, I say, a lot of time, a number of days, weeks, talking with our colleagues in software and systems, and indeed within certification and operations, to say, look, what is the data you're kind of expecting to see from us? How do you want to see it? How do you want it to be represented? And at that point, we were able to make an acquisition decision, and we bought a tool in to then capture and do all this. So at that point, this really got us up to probably August, September of last year, which is where I kind of finished the original paper this was presented at. And where were we then? And it's pretty much where Animal Dynamics were at the end of last year. And that is, we've deployed the tool set, we've embedded the processes within it, the architecture is up and working. We've developed the set of views that we're using. So if you look down at this left-hand side, there was an initial set of 12 viewpoints or windows into the model, each representing various stakeholder needs, from the upper level stakeholder needs, to some operation analysis, to a regulatory view, to a training and support view for potential customers. And of course, the design, the validation itself for the system. And they all get represented in some kind of visual format using this system or notation. But also you've got a further set of views that sort of go into the more of the detail of how you're delivering that viewpoint. Each of which is expressed in a diagram, and this particular one, not too visible on your screens, I would guess, represents broadly a set of requirements here for autonomous operations. And all of that is informing the system design. And how that works currently is all of that informs, along with the information we're getting from the development of the flight control model, the dynamic control model that we're developing alongside this, and using some flying concept vehicles. So you can see one of those up in that right-hand corner now. It's not an artificial picture at all. All of the pictures you've seen of the parafoil glider are all in-flight images. And we use the data that we get from those flights to validate our models. So every flight goes out with a set of test criteria we want to see, and we bring those findings back in, and we use that to influence the design, and we use it to take back from the design back into the dynamic control model. And we're ongoing stress testing at the time that I departed in late December, still ongoing in stress testing that within an embedded project called the Stork M project. I also mentioned that I had this concept that going into this, that we were going to look at what was generic in terms of functionality across a number of potential future designs, whether they were parafoils, fixed wings, quad rotors, tilt rotors, or flapping wings, all of which that we've been exploring to some degree or another. And we've identified 14 potential functions that we think would be required of any air vehicle that we design. And if that holds true as an assumption, and we've gone to the extent of being able to describe each of one of those functions in some detail now, then we should be able to capture and model that functionality. And at future project kickoff, we're not starting from a bare model. We're going to inherit that model and inherit that architecture with us and specialize it for the exact requirement set. So ongoing stress testing, really trying to push the boundaries of what we could achieve with a parafoil glider type concept vehicle, exploring beyond visual line of sight, getting that detect and avoid system that we're going to need in order to deliver that beyond visual line of sight, safe, fully autonomous beyond visual line of sight, and really trying to fly when others can't. A lot of drones at the moment are limited in the environmental conditions in which they can operate. We really want to stretch the boundaries of that. There's not really many reasons why, for example, a parafoil can't fly in some pretty serious wind and rain conditions. In fact, to a degree, the more wind, the more lift we get. It comes with other sort of constraints. But it's not just simply about flying vehicles. Animal Dynamics is literally that. It was about looking at truly animal-inspired robotics. And ongoing research goes on into things like flapping propulsion, water-based vehicles, and a really novel project that we were doing with DSTL that I won't go too much into even in the Q&A here, about using magnetic field navigation underwater. Learning really from lobsters is the insight I'll give you to that, which involved one of our engineers having an incredible time of his life in a yacht off the Scilly Isles for about 3 months for part of last year. What animal dynamics was about is really evolving performance of man-made systems, particularly our man robotics, evolving our engineering and making all about using novel technologies and making it model driven right from the outset.